Okay. So yeah. So till last class, what we did was, we learned a few new topics. So last class, I think we learned how to, uh, you know, so there are no recorded course like mechanical electronics at least. Okay. Yeah, I'll try to take this point to the person in charge for this. As I said, we are basically just PhD students, and like doing more than one classes per week is will hinder our progress in our PhD. So for at least for the individual like me or the other person who's like taking this NPTEL course with me, who's Rahul, you know, doing more than one courses per week is not that optimum. But I will take this point to the person in charge and see if we can come up with any solutions. Okay, fine. So yeah, so okay. So till like for the last few classes, what we have been doing is we were looking into few new concepts, and we were trying to solve some questions with respect to these concepts. We'll continue doing that for a few more classes with regards to CRE. So last class we learned, the equations, how to arrive at the equations for series and parallel reactions, and how to how the optimum time for a series reaction behaves, how the concentration changes with time in series and parallel reactions, and so on. So today what we'll be doing is we'll be looking into multiple reactor systems. So last class we looked into multiple reactions. This class we'll be looking into multiple reactors or multiple reactor system. So when I say multiple reactor, there are obviously there are two possibilities. So actually there are four possibilities, or not four. You can have actually have more than four possibilities, but let's vaguely classify these into two possibilities. One is series, another is parallel. So you can have reactors in series, you can have reactors in parallel. So yeah, let's just get into this series and parallel systems. So what we'll do is first we'll look into CSTR in series, right? So let's take just roughly draw our system. So this is our CSTR1. We have an inlet. This comes out into another CSTR. This comes out, and it goes on. You can have say n number of CSTRs. We'll see how we can derive the equations for such CSTR systems in series. So let's take our inlet concentration as Ca0, and we let's say our flow rate is nu as usual. Let's number everything in this CSTR system with 1. So this is our CSTR1. So this is the outlet will be Ca1, right? And the Ca1 and with the conversion XA1. So this Ca1 will enter the CSTR system 2, and the outlet will be Ca2 with conversion XA2. And at n CSTRs we'll have CAN and XAN. So let's take this as our rough representation of a CSTR in series system. So one thing we need to note here is that we'll there is a reaction that happens minus, let's assume that the reaction is a first order reaction. Say something like A gives B, and the you can write the reaction rate minus Ra is equal to KCA, right? So let's say the K, the reaction rate or the reaction rate constants varies with these reactors. So let's say for system 1, we'll have Ra1 is equal to KCA1. So here it is minus Ra1, which is K1 CA1, right? So and in system 2, we'll have minus Ra2, which is K2 CA2. And for our nth CSTR, we'll have minus RAN, which is basically, KN CAN. So our assumption here is that this is a first order reaction for simplicity. You can derive this equation in the same procedure for, higher order systems as well, for second order, third order, and so on. But for the sake of our simplicity, we'll take it as first order with minus RA is equal to KCA or as our reaction rate. Fine. So what we'll do is we'll write the general equation for the design of CSTR. So CSTR design equation, we have tau is equal to Ca0 minus Ca by minus Ra, right? So this is our general equation for a CSTR. Okay. So we can apply this CSTR design equation for each of these CSTRs. So let's take CSTR1. So we'll have tau 1. So let's say tau 1 is the space time of the first CSTR. So tau 1 will be Ca0 minus Ca1 by minus Ra1. And if we expand this minus Ra1 as K1 Ca1, it will be Ca0 minus Ca1 by K1 Ca1. Okay. So if we rearrange this a bit, we can take this, uh, K1 to this left hand side, and we can write something like, tau 1 K1 is equal to Ca0 minus Ca1 by Ca1. Okay. Now if we take this Ca1 outside, and if we rearrange this a bit, we can actually write this as Ca1 is equal to Ca0 by 1 plus tau 1 K1. So did you guys understood how we did it? Okay, I'll do it anyways. So basically what we did is on the right hand side, okay. So basically, yeah, what we did is just, a rearrangement. Okay. What we did is just a basic rearrangement of, this equation. So where is it? How we do it? Yeah. So we just take this CA1 outside from this right hand side, and we'll have CA0 term in the bracket, and we just take it to this side, and just a rearrangement basically. So we'll have an equation CA1, which is equal to CA0 by 1 plus tau 1 K1. Um, is this fine? Okay. So let's say this is our equation. One second. Yeah. So let's say this is our equation for the outlet concentration from first CSTR. Now we can do the same thing for CSTR2. Okay. And we'll arrive at an equation CA2 is equal to CA1 by 1 plus tau 2 K2. You want me to write how we arrived at this equation? We just applied the design equation for CSTR2. So the inlet concentration for CSTR2 will be Ca1 and the outlet concentration will be Ca2. So we'll arrive at this equation Ca2 is equal to Ca1 by 1 plus tau 2 K2. Is this clear? Okay. So you can keep on applying now. Okay, before we move on to CSTR3, what we can do here is, so we have CA1 expression as, CA1 is equal to CA0 by 1 plus tau 1 K1. So what we can do is, we'll substitute this CA1 in CSTR2 with that equation. So CA2 will be CA1, which is CA0 by 1 plus tau 1 K1 into 1 plus tau 2 K2. Right? So this will be our general equation for CSTR number 2. Right? So what we did is, we just substituted CA1's term from our CSTR1 and we substituted it into CSTR2. Now we can keep doing this for n number of CSTRs. So I'll do one more CSTR number. So let's say CSTR3. We'll have CA3 is equal to CA2 by 1 plus tau 3 K3. And if we substitute CA2 from this previous CSTR2 equation, what we'll get is CA3 is equal to CA0 by 1 plus tau 1 K1 into 1 plus tau 2 K2 to 1 plus tau 3 K3. So this will be the equation for the outlet concentration from CSTR3. And if we proceed like this for CSTR number n, we'll have the general equation CAN is equal to CA0 by 1 plus tau 1 K1, 1 plus tau 2 K2, and this will go on up to 1 plus tau n Kn. Right? So this will be the general equation for the outlet concentration from NCSTR in series. You can write the same equation for conversion as well. So in these cases, what we did is, we rearranged it to find the outlet concentration. So instead, you can use the same equation and you can find the conversion as well. So from this CAN equation itself, we can write conversion. So let's say, we have CAN. So XAN conversion will be 1 minus CAN by CA0. This will be the conversion, right? So conversion is basically 1 minus the outlet concentration by inlet concentration. So the outlet concentration from this NCSTR in series system is CAN and the inlet is CA0. And for this CAN, we have the general equation here, right? So if we apply that here, we'll have this XAN is equal to 1 minus CAN, the CA0 and CA0 will get cancelled and it will be 1 minus 1 by 1 plus tau 1 K1, 1 plus tau 2 K2, and will go on till 1 plus tau n Kn. So this will be the general equation for conversion from a CSTR in series system for n CSTRs. Fine. So these, so if you are tasked with solving a CSTR in series system, you can apply these equations to find the outlet concentration and the outlet conversion. And the peculiar thing or the interesting thing here is, you can apply the design equation for each and every CSTR separately itself. So basically that's what we did here, right? The above written conversion formula is for, yes, it is only for CSTR. Yes, because the design equation that we use there is of CSTR's design equation, right? So see, we are using the CSTR design equation to derive this equation. If we wanted to do this for PFR, we have to use the design equation for PFR. So we will come to that actually. So this general equation that we just found here is basically only for CSTR. And as I said, the interesting thing is, if you come across a question where you have to solve such a system, let's say two or three CSTRs in series, and you only know the inlet concentration, you can apply this design equation separately for each and every CSTR. So here you see in CSTR1, we applied this design equation tau is equal to Ca0 minus Ca by minus Ra for just CSTR1. So we'll have the design equation like this: tau 1 is equal to Ca0 minus Ca1 by minus Ra1. So that is the design equation for CSTR1. You can do the same for CSTR2. So for CSTR2, it will be tau 2 is equal to Ca1 minus Ca2. Inlet concentration minus outlet concentration by minus Ra2. And you can use this design equations to solve such a system. And we'll look into this more in detail when we come across CSTR and series question. Okay. So yeah, this is the general equation for CSTR in series. Now, let's say let's take a special case. What if all the space times are same, and also all the reactions happen at the same temperature? So when all the space times are same, that means tau 1 is equal to tau 2 is equal to, these are all same, tau 1. And let's just take a general space time as tau. And if all the reactions that happens, so the reaction happening in CSTR1 is the same as the reaction that is happening in CSTR2. So basically what this means is minus Ra1 is equal to minus Ra2 is equal to etc. till minus RAN. And let's take the general term as minus RA. So what does this mean? This basically means K1, the reaction rate constant, is equal to K2 is equal to Kn, and let's take a general term as K. Okay. So what will the equation become when all the space times are just same? That means tau 1, tau 2, tau 3, etc. is just tau, and K1, K2, K3, etc. is just K. We'll look. So if the tau is constant and K is also constant, so let us write our general equation. Can is equal to Ca0 by 1 plus tau 1 K1 etc. till 1 plus tau n Kn. So when tau and K are constant throughout the CSTR system, then this equation will become Ca0 by 1 plus tau K into 1 plus tau K etc. up to n times 1 plus tau K. Or this Can will be Ca0 by 1 plus tau K the whole raised to n. This will be the general equation for this special case where tau and K are constant for all the CSTRs that are in series. And you can use this same equation to find conversion, which is Xan, that will be 1 minus 1 by 1 plus tau K the whole raised to n. Fine. So this is so these two are the general equations for concentration and conversion. Concentration and conversion when the space time and the reaction rate constants are constant throughout the system. Now Does anyone know why we prefer CSTR in series compared to just taking a single CSTR? I'll put you through this thing. So let's take two cases. So in one case we have a CSTR of uh, okay, to have better conversion. Fine. Um, Not exactly, but you are on the right line. So I'll show you how. So let's take case one. We have CSTR with our tau as, let's say, some 100 units, and let's take case two where we have um, four CSTRs in series. This one is a single CSTR, and in case two it is four CSTRs with tau 1, tau 2, tau 3, tau 4 as 25. So basically, the sum of these space times is 100 in both the cases. But in case one, we took that space time as a single CSTR. So it is a single CSTR with very large volume. And in case two, it is a series combination of four CSTRs with small volumes of 25, 25, 25, 25 each. So let's see how this affects our, thing. So in case one, so we looked at the graphical representation of these CSTR systems, right? So in case one, if we draw, um, you know, with respect to minus 1 by RA and conversion XA, in case one, this is our operating line, and this entire rectangle, okay, the entire area under this rectangle will be the volume of our CSTR, right? But if we take the case 2, we have the same operating line here. So this will be our operating line. And let's say, our first reactor gives a conversion of X1, XA1. And the second reactor gives a conversion of XA2. And the third reactor gives a conversion of XA3. And the fourth reactor gives a conversion of XA4. So now the area under this curve will be like this. So this will be the area for the first CSTR. This will be the area for the second CSTR. This will be the area for the third CSTR, and this will be the area for the fourth CSTR. So the area will be, you know, so the total area here will be like this. Now just tell me which case gives you the lesser area compared to case 1 and case 2. Yes, case 2 gives you the lesser area. So what this basically means is, in both the cases you are achieving a conversion, the same conversion. Let's say your conversion is something around 70% or 80% or whatever. In both case 1 and case 2, your final conversion is basically the same. But then in case 2, because you are employing the CSTRs in series by taking smaller volumes, so you took four CSTRs of space time 25 each, you are able to achieve that conversion in a much lesser volume compared to the first case. You get it? So that is basically the reason why people prefer to employ CSTR in series compared to take a single CSTR of huge volume. Now, Another thing that I want to mention is the case 2. So let's take let's take a huge number of CSTRs in series. Let's take infinite number of CSTRs in series. So what that essentially means is, you'll have a CSTR volume here, then you'll have a volume like this, then you'll have a volume like this, like this, like this. It will go on like this. Okay. Now this is essentially equivalent to a PFR, right? I'll show you. I'll take a new page and write it. So what did we learn in PFR? In PFR, the volume of the reactor is basically the area under this curve, right? This is the volume of PFR. And now for CSTR, infinite CSTRs in series, it is equivalent to this, right? So let's say you're taking a CSTR operating line, the volumes are pretty much like this, right? So in both these cases, the area is basically, the area under the curve. So here for infinite PF CSTRs, the area will be like this. So this is basically area under the curve only. And that is pretty much what is the area under the curve for PFR as well. So that is why we say, infinite number of CSTRs in series is equivalent to a PFR. Okay. So that is one more thing that I wanted to tell you guys. Okay, fine. So just a note in general, if your order of reaction n is greater than 0, PFR will give a better conversion compared to CSTR in series compared to CSTR of the same volume. Okay, so note that point. So if you have a PFR of, let's say, 10 meter cube or a space time of 10 units, and if you have a CSTR in series, let's say 5 CSTRs in series with two each, space times. So and then a CSTR with space time of 10. So I'll write it here. Space time of 10. This is, space time is equal to 5 CSTRs of 2 space time, and then CSTR also you have a space time of 10 for. So that means basically the total volume of PFR, CSTR in series and CSTR is constant here. In such a case, you will have a better conversion for PFR, then you'll have a decent conversion in CSTR, and you'll have the least conversion in, sorry, you'll have the best conversion in PFR. This will be followed by a decent conversion in CSTR in series, and then you'll have the least conversion in CSTR compared to these three. Okay, so when your order is greater than 0, so if it is a positive order reaction, so something like A gives B or A gives 2B and so on, PFR will be the best choice for that, and that is followed by CSTR in series. So if you are not able to do it in a PFR, CSTR in series is the next best option, and then only CSTR is the least preferred option. Okay. Now conversely, if your order is less than 0, so if it is a negative order reaction, okay, In that case, so for example, can someone just tell me what will be the reaction rate of a negative order reaction? Like just an example, if does anyone know? Okay, so okay, still, I'll show you. So let's say you have a reaction rate like this: Ra is equal to K by Ca, or this will be basically what K Ca raised to minus one. So what is the order here? The order is minus one. So if it is, something like minus Ra is equal to K by Ca cube, it will be K Ca raised to minus 3. So you must have seen a reaction rate of this form as well, where the concentration terms are in denominator. So such reactions are basically called negative order reactions. So just, letting you guys know here. So if your reaction is a negative order reaction, then this order will also be reversed. PFR will be the least preferred compared to CSTR in series compared to CSTR. Okay. And let's say if your order is exactly zero, it is a zero order reaction. In that case, it doesn't matter. PFR will be equal to CSTR in series will be equal to CSTR. Everything will give you the same concentration or conversion. So this is just a general note. It's good if it's better you note this because a lot of questions can be asked with this. So you'll be given three options, and the question will be like you have a first order reaction. Which reactor is the best, or sort these reactors in order of conversion and so on. So if you are given a first order reaction and you are asked which of these reactors give you the best conversion, then PFR is the answer. And if it is a negative order reaction, CSTR will give you the highest conversion. And if it is a zero order reaction, the conversion will be same across PFR and CSTR. Okay, fine. Now, what if we looked at CSTR in series now? Let's look at PFR in series. So PFR in series, let's take PFR like this, which has a space-time of tau 1 or a volume of V1. We have another CSTR like this, which has a space-time of tau 2 and a volume of tau 2, V2, and so on up to n PFRs. Okay, so you know the design equation for PFR, right? So design equation for PFR tau is basically integral of minus dCA by minus RA from CA0 to CA, right? So let's take the inlet concentration as CA0, and this will be CA1, this will be CA2, and the final nth PFR you'll have CAN with tau n and Vn, right? So what happens here is, so if you write the design equation for the first PFR, tau 1 will be integral of CA0 to CA1 minus dCA by minus RA, right? Or you can even write it as RA1, up to you. And we'll take that assumption here that uh, the reaction happens at the same temperature. So that means minus RA and K is constant. Okay, so we'll just take it as minus RA. Now if you write the same design equation for tau 2, it will be integral CA1 to CA2 minus dCA by minus RA. And you can write this up to tau n, which is basically integral of CA n minus 1 to CAN minus DCA by minus RA. Okay. So what this is basically tau. If you write the sum as tau is equal to tau 1 plus tau 2 plus tau 3 plus etc., which will give you your total results time. That is basically integral CA0 to CA1 DCA by minus RA plus it will go on till CAN minus 1 CAN minus DCA by minus RA. So this is basically CA0 to CAN minus DCA by minus RA. So I hope you guys are getting the significance. The significance here is if you have CSTR in series, let's say, you know, we have three CSTRs in series like this, and each of the space time is the volume is 10 here, and let's take the space time as 5 or whatever value. We'll just take volume here. So we have the first CSTR volume as 10, the second CSTR volume as 15, and the third CSTR volume as 20. This is basically equivalent to you having a PFR which has the total volume. So 10 plus 15 plus 20, that is 45. So these two are same. So that is what this equation denotes here basically. So if you are having multiple PFRs in series, that is basically equivalent to you having a pretty large PFR which has the volume as the sum of all these small PFRs volume. Okay. So earlier in CSTR, we noticed that, if you have CSTR in series, it will give you a better conversion or it will reduce your, volume required for the given conversion. Here in PFR in series, nothing of that sort happens. The volume will just get added. So if you have three CSTR in series or if you have a very large, if you have three PFRs in series, or if you have a very large PFR in series, as long as the total volumes are same, the conversion is going to be same. So that is the significance here. So there is no advantage of you using small PFRs in series, like how you had an advantage when you are using small CSTRs in series. Is it clear? Okay, fine. Now I'm taking a lot of time today. I wanted to take you through one more concept, but fine. Let's see. We'll start with the questions. Okay, we'll start with the questions, and then if we have enough time, or we'll look to this concept through series to the questions as well. So what I was saying is, so far we looked into CSTR in series and PFR in series as well. But what if you have a CSTR and PFR in series? Okay, so that is what I wanted to go through before we started the questions, but it's almost 6:50 already. So we'll just start solving these questions and let's see what happens. Okay, fine. So yeah, just go through this question and we'll see. Okay, before that, I hope you guys know what is a half-life of a reaction. I think I have taught it in the previous classes, right? Can anyone respond? Okay, yeah. So this question is based on half-life of a reaction. Yeah. Okay. So this question is based on half-life of a reaction. Just go through this question and we'll start solving it. Nice. Yeah, zero order reaction is the right answer. We'll look into how we got that answer. Okay. This is a question from GATE 2015 from Chemical Engineering. Question number 28. For which reaction order the half-life of the reactant is half of the full lifetime time for 100% conversion of the reactant. And the four options given are A. Zero order, B. Half order, C. First order, and D. Second order. So this is a question from reaction kinetics part from chemical reaction engineering, and the reference NPTEL series can be found in week 3, lecture 2, integral method of analysis of batch reactor data, part 1, chemical reaction engineering 1 by Professor B. Mandal, Department of Chemical Engineering, IIT Guwahati. So to proceed to this question, let us first start by writing the general equation for nth order reaction. So for n order reaction, the general equation is 1 by Ca raised to n minus 1 minus 1 by Ca0 raised to n minus 1 is equal to n minus 1 into Kt. Or we can write this as Ca raised to 1 minus n minus Ca0 raised to 1 minus n is equal to n minus 1 Kt. Now, there are two cases given we'll have to take here. Case 1 is the half-life case where the reaction proceeds to 50% of the conversion. That means conversion is 50%. Or this also implies the final concentration Ca is basically Ca0 by 2. So for nth order reaction using this, we can write Ca0 by 2 raised to 1 minus n minus Ca0 raised to 1 minus n is equal to n minus 1 into Kt. Let's take this as our equation 1. Now, the second case, case 2, it is full time. That means conversion is 100%. This also means Ca will tend to 0. That means all of A has gotten converted into the product. So Ca will be 0. So the general equation Ca raised to 1 minus n minus Ca0 raised to 1 minus n is equal to n minus 1 Kt, and the Ca term will get cancelled and our equation will become minus Ca0 raised to 1 minus n is equal to n minus 1 into Kt. So let's take this as our equation 2. Also, we need to note that the time is different. So in the first case, it is n minus 1 into Kt half, and the second case, it is n minus 1 into Kt. So we have two equations. Divide these two equations. So let's take 1 divided by 2. So what we'll have is, on the left hand side, Ca zero point 0.5 Ca0 raised to 1 minus n minus Ca0 raised to 1 minus n by minus Ca0 raised to 1 minus n is equal to n minus 1 into k t half by n minus 1 into k t. Okay, so we can cancel out the Ca zeros in the left hand side in the numerator as well as the denominator. We can also cancel out n minus 1 k in the numerator and denominator respectively. So we'll get our equation 0.5 raised to 1 minus n minus 1 by 1 minus 1 is equal to t half by t. So here in the question, they have asked that half-life of the reactant is half of the full time of the uh, time for 100% conversion. So that means T half is nothing but 0.5 into T. That means half-life is nothing but 50% of full time. So now all we have to do is substitute this T half, which is equal to 0.5 T, in the equation. So 1 minus 0.5 raised to 1 minus n is equal to 0.5 t by t, and the t and t will get cancelled, and you can take this 0.5 raised to 1 minus n to the other side and 0.5 to the left hand side, and it will basically become 0.5 is equal to 0.5 raised to 1 minus n. Now we can take logarithm or ln. It will be ln 0.5 is equal to 1 minus n ln 0.5. So this ln 0.5 and ln 0.5 and both the sides will get cancelled, and this will be basically 1 is equal to 1 minus n. And all we have to do is solve this equation for n. Concept is pretty much the same. Just write the equations for half time and lifetime. Just divide these two equations and you will get only one variable to solve, that is n. And when you solve for n, you will get n is equal to 0. So that is the concept here basically. Fine. Okay. Fine. Let's do one more question, a simple question, and we'll stop for this class. Okay, just go through this question. This is a question from the shifting order reaction. We have learned this question, we have learned this concept in the previous classes. Just go through this question, we'll solve it in a minute. Okay. So there's a question from GATE 2015 from Chemical Engineering, question number 28. An irreversible homogeneous reaction A gives products has the rate expression rate is equal to 2 Ca square plus 0.1 Ca by 1 plus 50 Ca. where Ca is the concentration of A. Ca varies in the range of zero point 0.5 to 50 mole per meter cube. For very high concentrations of A, the reaction order tends to, and the four options given are A 0, B 1, C 1.5 and D 2. So this is a question from reaction kinetics, and the reference NPTEL series can be found in week 4, lecture 1, Integral Method of Analysis of Batch Reactor Data, Chemical Reaction Engineering 1 by Professor B. Mandal, Department of Chemical Engineering, IIT Guwahati. So this question, this order is called as shifting order. So what shifting order basically means, for high concentration, you will have a different order, and for low concentration, you will have another order. So for in this question, they have asked us to find what is the order of this reaction at high concentrations of A. So let us see how we can proceed with this. So first, let us write down our rate equation. Minus Ra is equal to 2 Ca square plus 0.1 Ca by 1 plus 50 Ca. So here Ca is very high. So what this basically means is, in the numerator, 2 Ca square will be a lot more greater than 0.1 Ca, and in the denominator, 50 Ca will be a lot greater than 1. So what we can do is we can cancel out these low value terms from the rate equation. So we can cancel out this term 1 and this term 0.1 Ca from our rate equation, and we can rewrite our rate equation approximately as minus Ra approximately equal to 2 Ca square by 50 Ca. So this will be an approximation for our rate equation when concentration of Ca is very high. So rewriting this, minus Ra will be 2 by 50 into Ca square by Ca, that is Ca. So this is of the form minus Ra is equal to K Ca, and the power of Ca is 1. So at high concentrations of Ca, our reaction order will be tending towards 1. So the right answer here is option B, 1. Okay. So that is the thing. Yeah, someone said the answer 1. Yeah, that is right. So yeah, you guys have done this question previously as well. So I hope you guys understood what we did here basically. So we just depending on the concentration term, if the concentration terms are high, we'll just neglect out the other terms, and if the concentration terms are very low, we'll neglect the concentration terms, and then we'll find the order of the reaction. And these such kinds of reactions are called shifting order reactions. So the order will shift with respect to the concentration of the reactant. Is this question clear? Okay. So I wanted to try one more question. And this question basically, combination of reactors in series, CSTR and PFR in series. So since we don't have much time left, I'll stop here. What we'll do is we'll start the next class from this portion, combination of reactors, and then we'll see how we can proceed from that. Okay, fine. So yeah, thank you for joining, and I'll see you guys next Monday during Diwali day. And I wish you guys a happy Diwali.